Welcome to this scientific lecture on how the gas laws were discovered. Today we're going to explore the experimental methods that led to Boyle's law and other fundamental gas laws. This isn't just history, it's a practical guide for how you can approach experimental science. Let's set the stage. It's the 1600s. Scientists are just beginning to understand that air has weight and can exert pressure. Robert Boyle, working in England, is about to make a discovery that will change physics forever. The fundamental question Boyle asked was simple but profound. If I squeeze a gas, making it take up less space, what happens to the pressure it exerts? Why is this question important? Because if we can understand how gases behave, we can build better pumps, understand breathing, predict weather, and eventually build engines and refrigerators. So how did Boyle actually measure this? He used a J-shaped tube, sealed at one end, open at the other. The tube contained a sample of air trapped by a column of mercury. Here's a simplified diagram of Boyle's apparatus. The J-tube has trapped air in the sealed short arm. Mercury sits in the tube, and by adding more mercury to the open end, we increase the pressure on the trapped air. Here's the key experimental insight that every student must learn. Control one variable at a time. Boyle kept the temperature constant and the amount of gas constant. He only changed the pressure. What happens when we add mercury? The weight of the mercury column pushes down on the trapped air. This increases the pressure, and we observe that the volume of trapped air decreases. Now let's talk about the critical skill of making careful measurements. This is where most students struggle in the lab. To measure pressure, Boyle measured the height of the mercury column. The taller the column, the greater the pressure. He used inches of mercury as his unit. To measure volume, he measured the length of the trapped air column in the sealed tube. Since the tube has constant diameter, length is proportional to volume. Here's critical advice. Record every single measurement in a systematic table. Don't trust your memory. Write down the exact numbers immediately. Include units. Note any unusual observations. Here's what a real data table might look like. Notice the notes column. Maybe the mercury wobbled, or you noticed it was slightly warm. These observations matter because they help you identify sources of error. Let's discuss sources of experimental error, because understanding error is what separates good scientists from mediocre ones. First, temperature fluctuations. If the room gets warmer during your experiment, the gas will expand slightly. This is why Boyle worked in a temperature-controlled room and waited for thermal equilibrium. Second, mercury may stick to the glass walls. This creates friction and means the pressure reading might be slightly off. You can minimize this by using clean, dry glassware. Third, measurement uncertainty. When you read a ruler, you can't read it perfectly. Maybe you can read to the nearest tenth of an inch. This uncertainty propagates through your calculations. So here's the question. How do we deal with noisy data? How do we see the pattern when our measurements have uncertainty? The answer is, we plot the data graphically. Graphical analysis is your most powerful tool for finding patterns in experimental data. Let me show you why. Step 1. Decide what goes on which axis. Convention says the independent variable, what you control, goes on the x-axis. That's pressure. The dependent variable, what you measure, goes on the y-axis. That's volume. Here are your axes. Pressure on the x-axis, volume on the y-axis. Always label your axes with units. Is pressure in atmospheres? Inches of mercury? Pascals? Be explicit. Step 2. Plot each data point carefully. Use a sharp pencil or a computer. Each point represents a real measurement that took effort to obtain. Respect your data. Here are the data points plotted. Notice they don't fall on a perfectly straight line, but there's definitely a pattern. The points curve downward. Step 3. Look for the mathematical relationship. What curve fits these points? Is it a straight line? A parabola? Something else? The shape of this curve reveals an inverse relationship. As pressure increases, volume decreases. But it's not just any decrease, it's a specific type called inverse proportionality. How do we test if two variables are inversely proportional? Here's the mathematical criterion. If P is inversely proportional to V, then P is proportional to 1 over V. This means P times V equals a constant K. If we multiply each pressure by its corresponding volume, we should get approximately the same number every time. Look at this analysis. When we multiply P times V for each data point, we get 12.0 every time. This is strong evidence for inverse proportionality. This is Boyle's law. But real data is never this perfect. In reality, you might get 12.0, 11.8, 12.3, 11.9. There's scatter in the data. So here's the question. How much scatter is acceptable? How do we know if the pattern is real or just random noise? The statistical approach is to calculate the mean and standard deviation of your P times V values. If the standard deviation is small compared to the mean, you have a good relationship. If the standard deviation divided by the mean is less than 0.05, that's an excellent fit. Less than 0.10 is acceptable for student labs. Now I want to teach you a powerful technique called linearization. This makes pattern recognition much easier. The problem with curves is they're hard to fit by eye. It's difficult to judge if points follow a hyperbola or some other curve. But straight lines are easy to recognize. If points fall on a straight line, you know immediately there's a linear relationship. Here's the trick. Instead of plotting P versus V, plot P versus 1 over V. If Boyle's law is correct, this should give a straight line. Why does this work? Because P equals K times 1 over V. This is the equation of a straight line, y equals mx, where y is P, x is 1 over V, and m is the slope K. Beautiful! Now the points fall on a straight line. The slope of this line is K, the constant in Boyle's law. This linearization technique is used throughout science. Now let's move to another gas law, Charles's law. This relates volume to temperature. The experimental approach is similar, but with important differences. The new experimental challenge is controlling temperature precisely. We need to heat or cool a gas sample and measure its volume at different temperatures. A typical setup uses a cylinder with a movable piston. The gas is inside the cylinder. We heat it with a water bath or heating element. As temperature increases, the piston moves up, showing volume increase. Critical point. We must keep pressure constant. We do this by using a freely moving piston that can slide without friction. The atmospheric pressure stays constant, so the gas pressure stays constant. We measure the volume at different temperatures. Start cold, maybe 0 degrees Celsius, heat gradually to 20 degrees, 40 degrees, 60 degrees, and so on. Here's the data table. Notice I've added a column for temperature in Kelvin and a column for V divided by T. This ratio is constant. This is evidence for direct proportionality. Charles's law states that volume is directly proportional to absolute temperature when pressure is held constant. Mathematically, V over T equals a constant K. Notice we must use absolute temperature in Kelvin, not Celsius. Why must we use Kelvin? Because proportionality only works when 0 on your scale means 0 of the quantity. 0 Kelvin means no thermal energy. 0 Celsius is arbitrary. This leads us to one of the most profound discoveries from gas law experiments, the concept of absolute zero. If we plot volume versus temperature and extrapolate the line backward, we find that volume would reach zero at negative 273.15 degrees Celsius. This is the extrapolation. The line crosses the x-axis at negative 273 Celsius. This is absolute zero, the coldest possible temperature. Below this, volume would be negative, which is physically impossible. What's remarkable is that this prediction was made from room temperature experiments, long before anyone achieved temperatures close to absolute zero. That's the power of careful experimental science and mathematical analysis. Eventually, scientists combined Boyle's law, Charles's law, and other relationships into one master equation, the ideal gas law. PV equals nRT. Pressure times volume equals the number of moles times the gas constant times temperature. This single equation unifies all the simple gas behavior we've discussed. It's one of the most useful equations in chemistry and physics. But remember, this equation came from careful experiments, not from theory. Boyle didn't derive his law mathematically. He discovered it by making measurements and looking for patterns. Let me give you practical tips for when you do gas law experiments in your own lab. Tip 1. Wait for thermal equilibrium. When you change the temperature, wait several minutes for the gas to fully equilibrate. Rushing leads to bad data. Tip 2. Take multiple measurements at each condition. Measure the volume 3 times and average them. This reduces random error. Tip 3. Work with a partner. One person controls the equipment, the other records data. This prevents systematic errors from how you read the scale. Tip 4. Check for leaks. If gas is escaping from your apparatus, all your data will be wrong. Test your seals before you begin. Tip 5. Plot your data during the experiment, not after. If you see points falling far from the pattern, you know something went wrong and you can repeat that measurement. Finally, let's discuss the skill of recognizing mathematical relationships from noisy data. This is what separates experienced scientists from beginners. First, ask yourself, do the points suggest a trend despite the scatter? Even if individual points are off, can you see an overall pattern? Second, use the linearization test. Try plotting different transformations of your data. If one transformation gives a straight line, you've found the relationship. Third, calculate residuals. For each point, find the difference between the measured value and the predicted value from your proposed equation. If residuals are randomly scattered, your model is good. This is a residual plot. The residuals are scattered randomly around 0, with no pattern. This indicates a good fit. If you saw a curve in the residuals, it would mean your model is wrong. Fourth, use your scientific judgment. Does the relationship make physical sense? If you conclude that pressure increases with volume, you should question that, because it contradicts what we know about gases. Let's work through an example problem. A student performs a Boyle's law experiment and gets the following data. Let's analyze it together. Here's the data. First step, calculate P times V for each trial. 1 times 2.4 equals 2.4. 1.5 times 1.65 equals 2.48. 2 times 1.18 equals 2.36. 2.5 times 0.98 equals 2.45. The mean of PV is 2.42. The standard deviation is about 0.05. The coefficient of variation is 0.05 divided by 2.42, which is about 0.02 or 2%. This is excellent agreement with Boyle's law. A 2% variation is well within experimental error for a student lab. This student did careful work. But what if trial 3 gave PV equals 3.2 instead? That's 30% higher than the others. This is called an outlier. When you see an outlier, investigate. Go back to your lab notebook. Was there something unusual about that trial? Did you record the wrong number? Was the temperature different? Don't automatically discard outliers without good reason. Sometimes outliers reveal real physics. Maybe the gas started to liquefy at high pressure. That's important information. Let me step back and discuss the broader lesson about scientific method that these gas law discoveries teach us. Science progresses through careful measurement, not just clever thinking. Boyle could have philosophized about pressure and volume forever, but only experiments revealed the truth. Mathematics is a language for expressing patterns in nature. The inverse proportionality of Boyle's law is a mathematical relationship discovered in experimental data. Graphical analysis reveals relationships that are invisible in tables of numbers. Always plot your data. The human visual system is excellent at pattern recognition. Experimental error is unavoidable but manageable. No measurement is perfect. Learn to work with uncertainty rather than being paralyzed by it. Simple laws often have limited ranges of validity. Boyle's law works for low-pressure gases, but fails at very high pressures when gases liquefy. Understanding these limitations is as important as knowing the law it's. Let me summarize the key takeaways for students conducting gas law experiments. 1. Control variables carefully. Change only one thing at a time. If you change both pressure and temperature, you won't know what's causing the volume change. 2. Record all measurements immediately with units and notes about conditions. Your lab notebook is your scientific memory. 3. Plot data as you collect it. This lets you spot problems early while you can still fix them. 4. Look for simple mathematical relationships. Nature often follows simple patterns. Try direct proportionality, inverse proportionality, and quadratic relationships first. 5. Use linearization to test hypothesized relationships. Straight lines are easy to recognize and fit. 6. Calculate quantitative measures of fit quality like standard deviation and residuals. Don't just eyeball it. 7. Question outliers, but investigate them rather than automatically discarding them. They might be telling you something important. Let me leave you with some final thoughts about the nature of scientific discovery. When Boyle did his experiments, he didn't know he was discovering a universal law of nature. He was just curious about how air behaves. Discovery often comes from curiosity, not from seeking grand theories. The process of careful measurement and analysis matters as much as the final result. Even if you're repeating a known experiment, you're learning the methods of science. Every great scientist started as a student, making careful measurements in a lab. The skills you develop now, controlling variables, recording data, finding patterns, these are the foundation of all scientific work. When you perform a gas law experiment, you're connecting with centuries of scientific history. You're following in the footsteps of Boyle, Charles, Gay-Lussac, and countless others who built our understanding of nature one measurement at a time. The gas laws remain profoundly relevant today. They're used in weather prediction, scuba diving, cooking at high altitude, designing car engines, and understanding planetary atmospheres. What you learn in these experiments has real applications. Finally, remember that science is a human endeavor, requiring patience, care, and honesty. It's not about getting the right answer quickly. It's about asking good questions, making careful observations, and reasoning rigorously from evidence.